This is the stock, by the way. This is the stock at X. But a priori, there can be the same stock at different X. And not every, I mean, in the intersection of all the opens containing a point, there could be another point. So that other point has the same stock. That's maybe annoying. But that's why if you have a T1 topology, like the Zariski topology, or a Hausdorff topology, like the classical topologies, you can separate points. And then the stocks are much nicer corresponding to the points, of course, because you can always assume that this is really connected to the point in that case. So that is the stock. So this is an idea of replacing a point by a stock in the sheaf. And why, maybe I should say that, is the, how late is it?
It's just coming up to 12.
I have 5 minutes or what?
No, but I think we should perhaps give a little more.
Like as long as he wants.
No.
As long as he doesn't go into lunchtime.
No, I just want to make the connection with the functions. Why I'm using sheaf theory, because otherwise you will ask me anyway, I think. So as I said in the beginning, I'm throwing away things. I'm throwing away the field. I don't have functions anymore. But if I have sheaves, then I do have functions again, but do something which is not a field, but something else. Why is that? Well, and that's essential why I want the sheafification. In the whole theory, I cannot use, I can do that if you want. I can introduce a field and everything is over a field and we can have maps. But I want, as I said, don't want to use the real numbers for some time. So I don't want to do that immediately, as long as I can avoid it. And therefore sheaf theory is a good answer. So I want sheaves, not pre-sheaves. Why? Well, you can prove that every sheaf, so you have some space, non-commutative or whatever, post set. You have some category. And the sheaf, the category of sheaves, with values in this category. So you have the pre-sheaves, and intermediate you have the separated pre-sheaves. Every sheaf is separated, so there is in fact, there's sort of something like this. Yeah, I'm watching everything. Okay. So the separated pre-sheaves are a torsion-free class of a torsion theory again. Supposing that this is a nice category, BLM additive or Grothendieck or whatever. So then you can view this as the torsion-free object for, and then this can be a localization of that. So this is what Grothendieck in the commutative case calls the sheafification functor. See, the category. So this is in Giraud's notation a reflector, and in the commutative case, but also in the non-commutative case, just the same. This is a, what is this? This is the localization functor corresponding to this torsion-free class. Torsion-free, you also know what torsion means then. These are, well, torsion is the things that sheafify to zero. But it's easier to work with the torsion-free case because separated has a meaning in the, you just define it. So the separated ones are a torsion-free class for the torsion theory. If I localize with respect to this torsion theory, I get the sheaves. Now there's one thing, in the non-commutative case you can do exactly the same. So you can take this category, the pre-sheaves inherit the properties of this category. That's just as good a category. So if this was Grothendieck, then the pre-sheaves over X with values in the sheaf, in the category, is also a Grothendieck category. So you apply the same technique and you get something that is a sheafification in some sense. But this is a categorical thing, and that's why I said I'll throw away the categorical things, because I have no relation with points anymore. And how does, in the Grothendieck theory, you construct the sheafification more or less topologically by constructing the étale space. There's an étale space. How do you do that? It's very easy. You take all the stalks, we have X, you have a pre-sheaf P, Px the stalk, let's say, Pu the sections. These are the objects in the category for the open set, these are the objects for the points, stalks, and sections determine each other for a sheaf. And how do you make the étale space? You just take the disjoint union of all the Px, you call that E. You glue the sheaves together, well, disjointed first, and now you glue it by defining a topology. You have a projection to the space X. So let's draw this as a big, a farmer kind of sheaves, the haystack, more or less a haystack. So here is a point S in Px, let's say, be a little bit careful, but it projects to x. So you have a projection that in every stalk you project to the foot point. And then this projection is easy to define, let's call it P, small p or pi. And now you have to define a topology here. Well, make this maps local homeomorphisms. So define the topology on the état space, making P into local homeomorphism. So there's a very coarse topology here, where the open sets are very flat, as I shouldn't say coarse. Open sets are really flat because they look like the open sets here locally. So in a small neighborhood here, there is a small germ of a function, if you want, here, that is homeomorphic to that small neighborhood.
What is like a small what? Word
The neighborhood here, if you go close enough to the point, then there is an open here that is homeomorphic to it. So I draw it as a line, because I draw this as a line. So in this fat covering of this topological space, I just take the small, it's small enough neighborhoods, I just take homeomorphic images. So I make it, this has a name in topology, but I forget, is it some initial topology of, well, whatever. I make this map into a local homeomorphism. So these things, the thing in the stalk you should think of is not just a point in this thing, it's a germ of function. It has infinitesimal information about what happens, because of, in fact, this topology reflects that. So it's germs of functions. And you see, germs of functions refer to functions, and I never used any functions. So what you get is that when you can make an état space, then every sheaf is a sheaf of functions to the, you can use this état space. So it is a theorem, I don't know, maybe due to Grothendieck, that every sheaf is a sheaf of functions. So for every sheaf S on X, there exists a Y such that S is the continuous functions from X to Y. Right? So I get functions, but not to a field. I get to the état space or something. I can construct them. So this is a first, of course you may say that's not enough. Okay, then if you absolutely want to introduce a field, I cannot stop you. And then you're free to, but let me give one line of philosophy. And I'm beginning to believe this more and more. At first it was a joke. And so I think the laws of nature are infinite systems of equations over the integers with non-commuting variables, infinitely many non-commuting variables, and infinitely many, at least as many as elements in the complex field. So I want, so you have something like Z with, and then infinitely many non-commuting variables, and enough because I want the specialization to C and so on. So when I go to other number rings or fields, it's a specialization of the real thing to a calculation in your mind using these numbers. As a consequence, we introduce singularities. It's kind of place. So when you see a constant of Planck appearing, it means that you're not